So as PCO2 goes down, this CAP17O of O2 increases, and this is, you can use different models to show it. And this is shown in terms of jacking it up. So this is a small range in PCO2. This is jacking it up to, this is a log scale of PCO2 from 100 to, what is that, 100,000 ppm. And shows that generally your delta, your CAP17O decreases increases, of your delta, of your CAP17O of your O2 decreases with decreasing PCO2. So this has been used to, and proposed to be used as a PCO2 barometer in the past, which is something that we're always trying to get at. We're always trying to figure out what were PCO2 levels in the past. And this has been a really, really hard, there's been lots of creative, lots of very good PCO2 barometers, but we're always looking for more. And so this is basically, this relationship that this CAP17O of this O2 is actually ends up being a function of PCO2. This also depends on sort of knowing gross primary productivity, which is a hard thing to sort of get at. But if you can make reasonable assumptions for this, if we could somehow in the geologic record record atmospheric O2 and measure the CAP17O of it, then we might be able to get at PCO2. So what records atmospheric O2 in the geologic record? Or do you have another question?
I have a different question.
Yeah.
Like, is this assuming that the reactions in the stratosphere aren't changing as a function of the concentration of oxygen in the troposphere?
You have to, well, you basically, you come up with a box model, right? Of you basically assume that those photoelectric reactions, those are happening up, are you know, you assign some sort of fractionation according to them, right?
That's just like a constant.
You assign them, right? You know, so with all of these models, you have to make some sort of assumption that that's happening, but then you do change the flux. You change all of the concentrations and you change the fluxes. And a big flux that is really hard is this gross primary productivity, that this is flux out. That's a hard.
I was wondering, because it's like such a small scale, if that has a bigger effect when you assume that it's constant. The mass independent fractionation that's happening is very, it's very big. So I mean, all of these things, you have to do sensitivity analyses of all of them. Yeah, and so it ultimately does affect your error bars at sort of the end of what we know. But where we are, there's some intervals in time in the geologic record where we need everything we can get to sort of get PCO2 constraints. And so if you can get one, then you can use it as a suite of data to say, okay, does this make sense or not? Does anyone have any ideas of what would be recording materials that would record O2? The isotopic composition of atmospheric O2. Ice, yep, and that's have been used, yep. So ice that's actually a big one. And actually, and some of these small variations in the sort of recent, in the past 15 to 20 years, people who are leading the front in terms of the CAP17O story has been done in ice. So that's an active field of development. Anybody else? I'm a recorder of atmospheric O2. Are you? Yes. So why, right? So 20% of my, you measure my teeth or my bones, and 20% of that is my atmospheric O2 signature, right? So fossil teeth or eggshell, that's it, or bones, that's a big one, right? They don't go back all the way. So other things that, there's sulfates, there's other things that have recorded. Atmospheric O2 is a hard thing to record, but so sulfates, hydrogen sulfates, so this is like gypsum, iron oxides, and then animals are a big one. And so then phosphates. So this is something that we're sort of building on. There's been some papers that actually, so this is using barite, so barium sulfite. This is a paper from 2008. It's from Hu-Ming Bao out of LSU, who's using the 17O of these sulfates to actually get at PCO2 in the Archean. But Ben Passy and Huanting Hu, has a student on doing this in dinosaur eggshells. And so, and is building a PCO2 record from the Mesozoic based on dinosaurs. So anyway, okay, you can also use this just generally to think about productivity. We sort of talked about this, but you can say, okay, let's actually now think about, this is Boas-Luz's group, and these units are sort of confusing, but the same sort of idea. You basically come up with a series of box models, and then you basically can tweak it, but you can kind of imagine where it's going. You have the stratospheric transfer of 17O and 18O from O2 and O3 to CO2. So CO2 is getting some sort of weird stratospheric mass-independent signature. And you can use this sort of signature. You can think about the fluxes of CO2, the fluxes of O2, and then think about so in from the stratosphere, and then think about the fluxes out from the biosphere, and then functionally use this as a tracer. So this is a whole other field of research and how people are looking at
productivity on sort of a global scale. People also look at actually 17O and dissolved O2 in the ocean to look at productivity rates as well, because atmospheric O2 looks very different in Cap 17O from water and anything that's coming. So there's some interesting, so you have a natural tracer, and so if you're looking at fluxes and you can assume or measure your end members, then you can look at how it's sort of varying. So people have used this in terms of paleoproductivity from ice cores. So this is from work out of Michael Bender's lab in 2002. So looking at, this is the last 70,000 years, so the present to 70,000 years ago. This is the last, around the last glacial maximum about 20,000 years ago, where PCO2 went from, so this is 190 down here and 270 up here. There's also so there's a drop in PCO2, there's a drop earlier in delta 18O of the and there's an increase in this Cap 17O, okay? And this increase of this Cap 17O is attributed to productivity changes and also as a function of the relative input of of stratospheric CO2, okay? So I'm glossing over this to a certain degree, but I wanted to give you a little bit of a flavor of the kinds of different things that could be used. So deep time questions, but also in terms of active productivity questions. So anything in terms of thinking about both the oxygen cycle and the CO2 cycles in terms of the rates of which uptake. So this is how things are, ways of use. Yeah?
Sorry, I'm like a little confused. How is it a natural tracer if it goes back into equilibrium with, like, as it's coming out of photosynthesis?
Because, so it's a natural, so yeah, so everything that basically interacts with the hydrosphere or photosynthesis will reset it. Right. But the reason why it's because then you can start to look at fluxes, okay? So your flux out, so basically, so anything coming out from biology of that O2 is going to look like a 0 Cap 17O. But it's going to be mixing and exchanging, right, with that atmospheric O2, right, which has some sort of influence from that stratosphere, right? So you can tell, so you have an end member, right?
What are the two end members?
So the two end members are,
is it the stratosphere?
it would be the stratospheric, let's sort of see here. So stratospheric O2 is Cap 17O, O2 is negative 1.5, and this must be what these units are. This figure is, I'd have to look at the, darn it. Well, it must be per mil because this is, but stratospheric O2, so stratospheric O2 is low. The flux, yeah, this doesn't, yeah, the flux in, now I'm sort of getting, let's not, none of these graphics, I should have reviewed all these different graphics, but basically the stratospheric O2 has a distinct, is low in Cap 17O, okay? Anything that's basically the O2 is out is basically reset to 0. And actually, I think what he's done here is he's not using the hydrosphere as a reference, so this is why things look goofy. I think he actually might be using atmospheric O2 as a reference. Anyway, so this is why my units are sort of off. But anyway, this pool is different from this pool going out, and what you measure in the troposphere, in the free atmosphere, is going to be a combination of these two end members, and the proportions of them.
So you're assuming, like, going back in the geological record, the stratosphere is the same, is like a consistent number, and the biosphere is always 0. You can use whatever.
Yes. Yeah, and the stratosphere is going to be different enough, yes. Okay. So that's what going back in time, and if you're using it today in time in different pockets and this mixing and these rates, so if you have an area where productivity is high, right, and before it's completely, or you can look at mixing rates, like you can basically, you should be able to see where this photosynthesis is high and the productivity is high, then you should be able to see that the tropospheric O2 values are going to look closer to 0, right? They're going to be sort of closer back on that line. They're not going to basically see that stratospheric influence as much, okay? So sort of imagine these two end members of, like, you have your, whether it's in sort of CO2 or whether in O2, of the stratosphere is some weird thing that's going on, these mass independent effects. And any time that you have those molecules that are interacting and fluxing through either the biosphere or the hydrosphere, they get reset to 0. Okay, and so then if you know those two end members, and then you don't know a flux or you don't know a concentration, then you can use those two end members as in some sort of mixing or box model to construct them. Okay, and the benefit is that you could technically measure 17O in CO2 and in O2. Yes, now I'm remembering this. everything is referenced to relative to 17 of the troposphere is 0, where this is actually negative 0.3 per mil relative to the atmosphere. So they've set their reference frame to be nutty, which is another thing in these CAP 17.0 studies, is that you always need to know what is your reference frame, and people change it around. And as this field matures, we have to actually start to use more regular terminology. But the field has been developed in so many different groups that it's like, I don't care, I'm just going to define the reference frame that works for this paper, which was this reference frame that worked for this paper is setting the CAP 17.0 of the tropospheric O2 to 0, right? And making that biosphere plus 155 per meg. That must be what it is. So, yeah.
You said that like this kind of model works on a constant 0 from the biosphere, and then stratosphere also having a constant value that's different from 0, right?
The constant value, so the reactions, the stratus, you can basically assume a set of the photochemistry of the mass independent. So it's not necessarily constant because it's going to be a matter of the concentrations of the CO2, but the CO2 that you will generate, these reactions are going to be constant, but it's going to be a matter of their concentrations.
Okay, so how do you know that stratosphere and member?
Yeah, you send a rocket up and you measure it, right? So people are measuring this now. And you talk to people who study the stratosphere, they're like, we don't really understand stratospheric mixing of CO2. So we're sort of at the, so as with all science, you basically start simple, and then you realize where your models fail, and then then you do sensitivity tests, and you realize, is it important for me to know this? Do I really need to know it? And if it's yes, then you go down that rabbit hole, and you figure it out, and you come out your rabbit hole, and you answer your question. So we're sort of at that point where like, wow, we can make these measurements now. Like, holy cow, there's a lot more variation than we thought. Do we care about this? Is this variation on a scale that it matters for our models? And then we have to come back and feed it into those box models and say, yes, it does matter. Or like, oh man, no, it's when it's actually not. It is sensitive or it's not sensitive. So, but this is how these fields kind of develop. Yeah.
But if you're looking at past climates, you can't send a rocket.
We can't, and there is the rub of geology. So we have to make some sort of assumptions, but we can know that this basically, the physical chemistry is, we should assume that it's relatively consistent. And, so we make reasonable, responsible assumptions, and we're always questioning them and evaluating them. Yeah. So the error bars are big. So I know when people work in modern systems, we're like, how could you possibly attempt to do that in the geologic record? It's like, well, we try to constrain the variables as much as possible and then go ahead. And in the end of the day, when you do that, sometimes, when really big things happen in the geologic record, they look like that. And you're like, okay, something happened there, right? And so when things look messier, you're like, so you basically, you try to tackle things that are really the obvious we call them slam dunk problems. And you want to find those slam dunk problems where the noises of all these things sort of get washed out. So that's some of the challenges of this, okay? So hopefully that will sort of give you a taste of that. All right, so now I'm going to move into that gray ellipse. All right, so all of this, there's lots of really exciting fractionation and big signatures, and this is what people had focused on in the past. But I'm going to now move into thinking about mass-dependent triple oxygen isotope variation and what we can get out of that. Okay. And part of maybe sort of before I, sort of thinking about all these kinds of things, this has been a real education for me in terms of you have to sort of be willing to be like, I don't know how this works, but let's learn about it, and let's learn about this kind of chemistry, and let's sort of understand how. So I still read a lot of these papers, and I'm just sort of like blown away and have to reread them and read them again. But it's an exciting field because it's a discipline that we're constantly trying to understand, and there's now lots of different people from different disciplines tackling it. Okay, so and who knows, maybe people, we've been assuming that that everything that happens in the biosphere is just 0, right? And I'm actually going to tell you that it's not 0, right? So how much does it have to deviate from 0 in the hydrosphere for it to make an impact on these other studies, right? So I have my own reasons for doing it, but it's always good to be sort of aware of this community and what other people are using this for, so we can sort of feed into it. So it's a very exciting science to be in, and I know that and with all these other isotopologic systems, there's also other very exciting pieces of science to be in.